Hello, welcome. My name is Kevin Ford. I'm a practice lead of emerging technologies at Cognizant Softvision. And welcome to week, or at least day 5 of Programmers Week. And I've been doing work in this field for about 30 years, at least programming in general. And today we're going to be talking about a developer's primer to AI and ML. And really what we're going down to is if you've heard of AI and ML in particular, and you want to know how it works, that's what we're going to be talking about. We're not necessarily going to be going deep into the math. The math could be several weeks worth of classes in and of itself. Also, if you've been doing AI work and ML work in particular for the last several years, these concepts are going to be somewhat basic for you. So today we're just going to be saying, hey, what is AI? What is ML in particular? How does it work? How do we come to the conclusions that we do? And if you're a developer, how can you use them in your applications? And in some cases, how can you make models of your own? So let's talk a little and do some level setting on what AI is. And artificial intelligence in general is when the computer is doing tasks that's normally reserved for human intelligence. And this has always been a moving target throughout time. If we went back to the 1950s, simple addition, simple multiplication, in some ways would be considered artificial intelligence. This is something that hadn't been done by machines, at least not widely done by machines until that time. It wasn't until the 70s that calculators really started becoming popular. And after that, it moved on to decision support systems and procedural programming, and all the things that had before been really considered artificial intelligence had kind of moved into the background of table stakes of normal development and working on computers. And now where artificial intelligence is really at, and what the kind of pinnacle of it is today, at least what you normally see in business, is machine learning. And machine learning is a type of artificial intelligence where you're trying to gain insights out of the data or use data to make predictions on what data will be in the future. So how do we do machine learning? What's in this cauldron here that we're trying to figure out? And if you remember way back to when you were in high school and even college, and you were learning calculus and statistics, and you may have gone on in your programming career and realized, you know what? I'm doing just a bunch of mathematics that's just simple addition, simple multiplication. I'm doing financial systems. Why did I learn this stuff? And I had been in my career probably like 25 years and wondering that same thing. And then finally I'd start doing machine learning. And it's like, oh my goodness, this stuff is actually useful now. I'm actually using statistics. And so I remember seeing a comic not too long ago where they had a bunch of guys in a street brawl, and somebody, the caption or it was, someone said that machine learning was just statistics. And there's a lot of statistics that's in machine learning, but it's not just statistics. Remember calculus? Well, there's a lot of that in there as well. So in particular, when you're talking about going down and figuring out back propagation and how to adjust your model over time to get it more accurate, you're probably using a lot of calculus under the hood. Once again, not going to go into the math on that. We could be here all week doing that. The other thing that's in there is trial and error. And so what I mean by trial and error, and this is particularly true of supervised learning, when you're training the model and you're trying to get it accurate, that actually is a process of trial and error. So it's trying to come up with a function that can, for example, predict whether there's a cat or not in a picture. And it goes through and it tries some logic out. It sees how accurate that is. And then it does some adjustments and it tries it again and again and again until you get a model that actually does predict whether or not there's a cat in the picture. Lots of data. And so you probably heard about this. Quote unquote, the more data, the better. And I don't know if that's exactly true. You'll need accurate data for sure. There is a minimum amount of data you need, but of course, the more data you have, the more CPU intensive the training process is. But in general, you want to have good, clean, accurate data and a sufficient amount of it in order to train your model. And the last thing we've got in there is a lot of repetition. I mentioned that going along with the trial and error is repetition, where we try things over and over and over again until we get a model that's reasonably accurate. Reasonably accurate. And we'll talk about that in a little bit, what I mean by reasonably accurate, because probably if you have a model, it's not going to be 100% accurate. So what is a model? So a model ultimately is just a function. And you're going to create a model when you have a situation where the logic is way too complex for you ever to figure out, right? So if we have a picture, and a picture is a collection of pixels, right? And you're saying, hey, is there a cat or not in that picture? And try to think of the logic that you have to do to figure out, based on the content of the pixels, if there's a cat in it or not. And I'm willing to bet that most programmers could not envision how to do that. I know I couldn't do it. I could not write a function from scratch that tells me whether or not there's a cat in the picture. Now, models are never going to be 100% accurate. In fact, if you have a situation where you need 100% accuracy, machine learning probably isn't for you. It isn't the right tool for the job. So I could technically write a model where the data that I passed in is, let's just say 3 + 5 = 8. And I could make a model that does simple addition that takes 2 parameters, returns out a result. And you probably wouldn't do that because we have better ways to do that. And also normally when we're trying to add 3 + 5, we want 100% accuracy. Where a model is going to say something like 3 + 5, I'm pretty sure the answer is probably going to be around 8.2. I don't know, somewhere in there, because it's not geared to do that type of accuracy and have those type of rules in it that are basically this input equals exactly this output every single time. If you need that type of accuracy, you're really looking back to doing something more procedural and doing your own logic. So models tend to solve a single problem. And if you think about like a machine learning model that's driving a car, that's probably actually several different models under the hood. I haven't actually written any such models to do car driving. I'm certainly not Uber or going, Elon Musk has not called me to make this happen, but generally I can take guesses what's happening under the hood. There's several different models. There might be a model to determine, for example, when to apply the brakes and how much brake should be applied at a given time. And it might be taking the speed of the car, and it might be also taking some information coming in from another model on objects that it detects where they are and how far away they are from it. It takes in the current speed of the car, etc., and tries to figure out how much of the brake to apply. And you can have several different models working in a system that have normal procedural logic that determines when to call each model and how to use the results of the different models. Finally, models can change if more data comes in, and you get this idea of reinforcement learning, and also the idea that the more data you have, the more accurate you can be. And as we talk about a model not being 100% accurate, what you're really saying is over time we have to have the expectations that the models will make mistakes, and as they make mistakes, we can make them more accurate over time because now we've got the data on the mistake. This is the information that went into the model. This is the result that came up with. This is the result it should have come up with, and we can retrain it and try to make it more accurate. And so this is actually one of the nice things about self-driving cars. If you come down to the idea that the model can be inaccurate in deciding when to apply the brakes, for example, just like a person can, sure, it might get into an accident, might hurt somebody or worse. But the nice thing is if you take that data, retrain the model, and that situation, you make it so it can't happen again. Unlike a human, you can now push that model out to every car so that it now knows in that situation how to handle it. Where with people, every person learns individually. And so you might make a mistake, and let's just say you hit the brakes too hard and you go into a soft patch of gravel, hit a telephone pole, for example. I'm not saying that happened to me, but if it did when you were a kid, you'd learn how to handle that situation. But each individual person has to learn that, unlike a model where all the cars could learn that at the same time. So generally, there's two real thoughts behind doing problems in machine learning. And there's this idea of unsupervised learning and supervised learning. And unsupervised learning is really the situation where you're trying to get insight out of the data and you don't know what answer you're looking for. You don't necessarily need labels in the data as far as what the results are because you don't know what the results will be. And so some examples of this are visualizations that you are doing in Power BI. We're actually taking the data and having it presented to you in such a way that you might be able to glean some insight about the data itself. And so that's unsupervised learning. And on the other side of that is supervised learning. And supervised learning, you actually have to go in and label the data, including the results. So you have to know the result you're looking for. So you might have something where you're saying, hey, we've got some pictures. We want to know whether we have cats in them or not. So we have 1,000 pictures and we've got them all labeled, whether or not there's a cat or not in each picture. And that's what you're using for your training data. And that would be supervised learning. Now, there are, or at least there is something called semi-supervised learning that is a kind of a combination of the two. We won't be talking about those today, but just be aware that it does exist. And that's basically where you're labeling some of the data, but potentially not all of the data. So if we go into unsupervised learning, this isn't a complete list by far, but these are some of the things that you can do in unsupervised learning. So for example, there's a concept called clustering. And under the covers, there's several different algorithms that go into this. Like I said, I'm not going to go deep into what these algorithms are, but just be aware that this idea of clustering exists. And so maybe you have a customer base and you've got 1,000 customers or 1,500 customers, and you've got some data about all the customers. You've gone through and cleaned it up, and you know how much they spend a year with you, you know what products they buy, et cetera, et cetera, et cetera. You can use clustering to say, hey, I want to know how to segment these customers. And so when I get a new customer and what segment they're probably in and how much that means they're probably going to spend with me, for example, what type of items they might buy. And the interesting thing about machine learning and the algorithm that will go through is you don't necessarily know ahead of time how it's going to split up the data. And even if you look at the data and let's just say it splits it up into 3 groups as we have visualized here in the upper left, you won't know exactly what criteria you used, or at least it used internally, to figure that out which group each one was in. What you do know is the data you fed it. You don't necessarily know how it came up with that result. Another type of unsupervised learning is a visualization. And you guys have seen these all the time. You guys are looking at a whole bunch of them right now on my screen. And a visualization is taking a bunch of data and putting it on the screen in such a way that the user can understand it. And so a tool you may have used is Power BI. So when they talk about Power BI and machine learning, what it's normally doing is unsupervised learning. We're giving it data. It's deciding on a way to display the data. And hopefully based on that display, you'll get some insights out of the data. Another type is dimensionality reduction. And what dimensionality reduction does is it takes complex data many times, and I've got an example here that's kind of 3D data, and takes it and splits it up in such a way that it's easier to understand. And sometimes you might do this so you can understand the data itself, or you might do it so that you can take very complex data and then feed it into supervised learning processes after you've taken the data and simplified it. Now, an association, that's another type, where you're going through and saying, if this, then likely that. And so if you think about going to Amazon, for example, and you look at some things and then suddenly it starts suggesting other things, or you put some things in your cart and it starts suggesting other things that maybe you want in the cart, probably underneath the cover, it's doing some unsupervised learning there with associations based on past buying behavior of people saying, hey, if he bought this or he's thinking about buying this, he's likely to buy that too. So that's an association. And the final one we'll just kind of mention today is something called anomaly detection. And what now we're looking at is how far off the normal certain data is in a series. And so we can use that in order to detect when some things potentially bad or unusual have happened in a set of data. And that might give us some predictive value on when things are going to happen again. So for example, if you've got some kind of device that you've been collecting data from, the device fails, and you'd go through some anomaly detection, you've got a bunch of anomalous readings right before failure, you might come to the conclusion that in the future, if you get readings in those range, you can probably be predicting that there's a failure happening very soon after. And you might even be able to use it if it's a time series to determine how far after the failure might occur. And so that's anomaly detection. Now, the nice thing about unsupervised learning is it's just taking the data and running through it once and giving you results. If you want new results, you can always feed it new data. It's a little different than a model, where a model is more like a function that we talked about earlier. So supervised learning generally comes in 2 flavors. And so we talk about supervised learning. Remember, this is where we know the answer and we want to predict future results when we put into our model. And the first type is a classification. And a classification is basically whenever you've got two or more buckets that you want to put your data into. So I gave the example of a cat or not cat. So you've got a bunch of pictures, 1,000 of them, and they're all labeled cat or not cat. That's a classification. It's a binary classification. You just basically have two classes, cat, not cat. And so we've got all this data in here about pictures of cats and pictures of other things that aren't cats, and it's all labeled whether it has it or not. So this is what a classification is. And so if you're doing like facial recognition, that might not only be doing some edge detection and detecting where a face is in a particular image. Once it has that result of where the face is in an image, you might put it through another model that's a classification to determine whose face that is, assuming that you have data on that particular individual and you know who it is. So facial recognition, for example, is exactly that, a type of classification. The second type that you're going to see a lot is something called a regression. And this is where you're taking a series of data and trying to predict something that might happen in the future. And so an example of this would be you're going down and you've got a bunch of data on how people have voted in the past. And then you've got a new person and you know how they voted in the past. And you want to predict what their result was on a different vote that they take, that you have information on how all the other people voted for. That might be a regression, right? So this isn't actually putting things into it's either this or that. It's saying based on this data, that's what I think the result is going to be for this particular situation based on all these other situations that we've trained it for. And presumably those situations will be similar. So we can have many independent variables, and these are the variables going into the model. These are the input variables into the model. And when I say many, you'll need at least two, right? Because if you have a situation where you've got one variable in and one variable out, chances are this is not really a candidate for machine learning. You've got some more traditional logic around this. But if you've got a complex set of variables, you don't necessarily know the relationship between the variables, but given this 5 or 10 variables, normally you can tell based on what they are what the result is going to be. And so we talk about an image classification. If we go back to classifications of image, the variables that are going in is actually the pixels. So the variables itself can be a lot of things, and there can be quite a few of them going into the model itself. So I mentioned in the bottom here, and I think I talked about this a little earlier, and the 4 plus 3 could be regression, right? So you got 4 plus 3, and that equals 8, and you got 2 plus 1, and that equals 3, and you got 8 plus 9, and that equals 17, and you could feed all this data in, and then you'll get a model that somewhat accurately will predict addition and problems. The problem is it's going to be 4 plus 3. It's going to say it's 7.1, 7.2. It's going to take a guess at where it is. It doesn't really know. The other thing with regressions is it's really looking for data that isn't necessarily exponential. It's looking for a straight line type of data. There's ways that you can get that in regression. So generally, it's looking for a direct relationship between all the variables. All right, so how are models made? So we've got this idea of a model, in particular with supervised learning. How do we make a model? How does it figure out, based on the data, what the future data will be? So first thing we talked about, you need clean and complete data. So a lot of times when you're making models, I don't know about your organization, but a lot of the organizations that I've seen, when you look at their data, is it clean and complete when you first look at it? And the answer is probably not. So a lot of the work of a data scientist right up front is going to be, all right, I got to clean up this data. I've got missing data. I got to figure out how to deal with that. Maybe I drop the data. Maybe I take some averages to figure out what the data probably was. But at the end of the day, you've got to figure out how to get clean and complete data and sufficient data to do our problem, and also relevant data. So for example, if you're trying to come up with a model that predicts based on particular new customers what their annual revenue they're going to bring into your organization is, and you start looking at whether or not the company name starts with A or not, is there a relationship between that and the amount of revenue they're going to bring in? I'm guessing probably not. So it's not relevant. So that wouldn't be a good input into your model. So you need some kind of relevant data. You got to really think, based on the problem that I'm trying to solve, what data probably tells me that. And it might be a little bit of experimentation on your part to figure that out. Now, one thing I hear a lot is how much data do I need? And so there's a lot of different answers to that. And I will say that on minimum, you're probably going to need about 10 times the amount of records as you have features. And a feature is those independent variables going into the function. And so if you have 5 different features going into the function, minimum, you're going to need like 50 records, right? Minimum. And that's probably, if you want a real accurate model, probably quite a bit less than you'll also need. Because also you don't want the same data 50 times, right? So you'll want a diversity of the data. You know, ideally, it would be great if you had one piece of data for every possible situation that you're going to cover. But having said that, if you really had that data, and so that you can tell for every particular number you're adding together, 4 plus 3, it actually equals 7. Well, you don't really need a machine learning model then either, because then what you've got is really a lookup table. So you need a lot of diversity of data, but just keep in mind that it doesn't necessarily mean you need to handle every possible situation. So for example, if we go back to our classification of cat, not cat, you don't need every single combination of pixels you can possibly come up with to tell you whether there's a cat or not in there, right? If you did have that, once again, you'd have a lookup table. So the data generally is divided into 3 groups. We'll talk about how this is used. And the first group is the training data. And this is the data that you're going to actually use to create the model as it goes through its initial process. And then once it's done with that initial process, it uses the validation data to say, all right, how accurate is my model or not? And then it'll do some adjustments. It'll go through some back propagation, and it'll figure out how to change the function and go through and try it with the training data again and see how accurate it is again, go against the validation data, and keep on doing that again and again and again. This is the repetition I talked about. And then finally, when you've got this model that you think is trained and trained well, you're going to take it against a new set of data that the model has never seen. Because remember, it's seen both the training and validation data during the training process, right? So this test data is data it's never seen. And now you can say, all right, based on these situations that it's never seen before, how accurate is it? And how accurate it needs to be is really dependent upon the business problem. So accuracy on determining whether or not something is somebody's fingerprint for security reasons probably needs to be very high. Trying to predict what the potential revenues are for a given new prospect, well, that doesn't need to be nearly as accurate as trying to do something like facial recognition or fingerprint recognition for security, or even that decision we talked about before on how much brake to apply in a self-driving car. That probably needs to be very, very accurate. So the training process actually goes in, and we've got our test data itself and a whole bunch of what they call trainable parameters. So you can kind of consider like the function that we're doing for our model, and we don't know the logic on how to create it. And so the function is going to train itself. So the function has a whole bunch of variables in it. And what we're going to do is we're going to set these variables. You can just consider it random for now. We'll set these variables randomly. It's going to multiply and divide and add depending on what the situation is. The information we're putting through in the test data, and that's going to be our training process where it's trying to make it more and more accurate. And then once it's done with that in one epoch, what we call an epoch, it'll go through and check the accuracy with our training data. It'll has a method that it goes through called backpropagation, where it decides how to change some of those parameters, and we'll talk about what those are. And then based on that, it'll go through it again and again and again. And your model should get more and more accurate over time. And then finally, you get your trained model out of it. And then you can compare that to your test data and see if it is indeed accurate enough with data that it's never seen before. So you might have heard of this concept of deep learning. And deep learning is something that works a little like our minds work. And I've got some pictures over there on the right of some potential neural networks. So when you hear deep learning, that's also a term that you might also hear as neural networks to refer to it. And we're not going to go through all of those. So I'm going to go through just a few of them that are really common that you might encounter and you might hear about. So when you think about deep learning, it's a way to do classifications and regressions. There's other ways to do it, but it's something that has really come to the forefront and is used pretty commonly today. And it is a subset of machine learning. And what it's going through, it's got something called neurons, which are individual calculations it does. And then it passes the result of that calculation to another neuron, to another neuron. And this is kind of similar to how our brains process data. And that's what it's trying to mimic. And there's a substantial amount of customization you can make to a deep learning model in order to get the result you want. In fact, you probably do want to do a fair amount of customization and playing around with the model parameters in order to come up with the most accurate model that isn't necessarily, we'll just say, overtrained. We'll talk about what I mean by that in a little bit. So here's our model. So we've talked about this a lot, right? So we've got our cats and not cat prediction model. So we're going to pass in our training data. And so for each record of the training data coming in, right, it's a collection of pixels and whether it's a cat or not a cat. So we have the input layer, and the input layer has some neurons in there. And those are displayed by those purple boxes. And we're going to basically have one neuron for each input parameter. So that would basically be one neuron for each number of pixels in our training data. And so that also basically implies that when we're doing this training, we're taking the pictures and we're normalizing them all to be the same size, right? Because we want to pass in, this is how it would normally work. And when we use the model later on, we'll convert the picture and make it the correct size for what it's expecting. So it's passing these pixels, and this is what's called a feed-forward network. And when we talk about a feed-forward network, what it means is the data just runs one way through the layers. And so we've got several different layers. We've got an input layer, that's those pixels come through. We've got an output layer, and I'll talk about why there's two neurons in there in a second. And then we've got a bunch of hidden layers. And that can be one or more layers you've got in there. And those might have different numbers of neurons in each layer. And generally in this type of network, it's going to take one neuron from the layer before and map it to every neuron in the next layer. And it's doing a math calculation on each one of these neurons. I'll talk about what that is in a second, but it's doing a math calculation on each one of these neurons. And so when you're going through this training process, and let's just say you've got, several hundred pixels going into this, and it's going through several hundred neurons in each layer, you can see that it's doing a lot of calculations under the hood. And so potentially to do this training process, it could require a substantial amount of CPU power. Now, on the output layer, we see that there's two neurons. And generally, the reason why I'm putting two neurons there is because I'm looking for two answers, whether it's a cat or not a cat. And I'm going to do some playing with those neurons to make sure that each one of those neurons is a number between 0 and 1. Maybe I'll use an activation function called a sigmoid. You guys don't necessarily have to know what that is today, but really just to know what it does is it maps data or a number between 0 and 1. So if you have basically 999 is the output number, that'll basically end up being a number very, very, very close to 1. So it'll be like 0.99999. And on the other neuron will basically be the inverse number of it. So if the top one that says is a cat is 0.95, the one that says that it thinks it's not a cat is going to end up being 0.05. And so what that's saying to us is it's about 95% sure that there is a cat in this particular picture that you pass through the model. So how does it figure out how to change and update the model? So we've got these parameters that goes through a whole bunch of calculations. It sees how accurate it is. And you might say, well, it's going to be like 50% accurate the first time. It's probably not. There's a reason for that. But you're trying to figure out how to update the model. And really what the model knows is two things, right? It knows the loss, right? And the loss is basically how inaccurate the model is. And also it knows the learning rate, which is basically saying how much to adjust the parameters each and every time we go through this training process. And so if we kind of consider, I've got a picture of Mount Everest here. This is one that I found that I thought was a pretty good example of it. We're at the top of Mount Everest and we're trying to get down to the bottom. And we're blindfolded, so we can't really see which direction we're going. So we know how, we've got an altimeter, so we know how high we are. And the altimeter is like how accurate or inaccurate our model is. And we know how big the steps we're going to take in each direction. So we might take a step in one direction. We look at our altitude. We've gone down some and we're like, woohoo, we're getting more accurate. So let's take another step in that direction and another step in that direction. And there's several different functions that determine how to adjust the parameters and which direction to take them. I'm not going to go into what all these are. There's a fair amount of calculus underneath the covers on these, but just be aware that there are those particular ones. And there's really two concepts that you want to think about. There's something called a global minimum. So the global minimum is you've got your model is accurate as you can possibly be, right? And then there's something called a local minimum. And that means that you've got your model somewhat accurate, but if you look all the way around it, if you change the parameters in any given direction, it becomes less accurate. But it's like a valley kind of in the middle of the mountain, right? So you're kind of at the bottom of the valley. Every way you step, you're actually going up higher, but you're not at the bottom of the mountain yet. And so there's ways that you can get around that. There's this idea of momentum. As you're changing things in one direction, we'll keep on changing things in that direction, even if it is getting a little less accurate, to try to get out of the valley. But that's just one thing to be aware of, and machine learning people have to be aware of when they're trying to train these models, is you can get caught in these valleys in the middle of your training process, and you end up stuck at like 85% accurate. You can't get it any more accurate. And then you start, well, maybe I need to take bigger steps. Maybe I need to play with momentum. Maybe I need to change my optimizer on how it's trying to come down the mountain. Now, there's a couple other ideas that you want to go into, and this is what's happening in each one of those neurons. And each neuron has a bias and a weight. And you can basically think of weight as how important the neuron is to figuring out the problem. And basically the bias is saying, well, it may be really important to come out with the problem, but the math as it is off from our desired result. And so we're going to add some bias on there, either a positive or negative amount, to make it come out to be the result that we want. And so each one of these neurons, right? So there could be, literally tens of thousands of these inside of our model that we're trying to train, which is our function we're trying to come up with, that has its own bias and weight. And so it's basically all just simple multiplication and addition to do these, but there's literally thousands and thousands and thousands of these calculations that are going on with each piece of data that we're putting through our training process. And this gets back into the idea of why you need some kind of reasonably powerful CPU in order to do the training. Now, once you've done the training, you've got your model, you can normally run it on much lower CPU spaces. That is to say, it's still going through all these calculations, but for each set of data, it's only going through these calculations once, and it's not trying to adjust them at that point. It's just trying to run it through the function and come out with the answer for the function. So as I remember, when you go through with the training process and it looks at the validation data and figures out how inaccurate everything is, it then goes back through a process to figure out how to adjust those weights and biases for each and every neuron inside of our model to try to come out with a more accurate model. So how do these pieces fit together? So we've got this training data coming into the input layer. And once again, if this is a picture, it's basically a collection of pixels. It might just be data on revenue or whatever it happens to be. Normally you want to convert it to some kind of numeric data so it can work with it easy. And there's lots of ways you can do it, including letters. You can convert to numeric data and convert it back coming out the other side. So on each one of the neurons, there's something called an activation function that gets applied to it. And this happens on each layer potentially. An activation function modifies the data. And so an activation function might say, for all the neurons in this layer, if the value is less than 0, just drop the less than 0 amount. And if it's greater than 0, just is what it is. And that would be actually an activation function called a reload. And if you remember, there's many different activation functions, and these are being called on every different neuron in the system. So potentially tens of thousands of times. And so when you're training your model, you might want to think about how CPU intensive the activation function is that you're doing. So a sigmoid I mentioned earlier on my last one is mapping things between 0 and 1. It's actually using, I believe, a sine function to do that. So that's actually very CPU intensive. Might be great in an output layer where you're only calling it a couple times, but in an input layer, or I should say in one of the middle layers, it might be very, very expensive to put it in there. And it's going through each one of these neurons, and then once it's all done and gets the result for the training data and what the training data is being calculated to be, it calculates the loss, how accurate or inaccurate it is. And if it's really inaccurate, it'll, well, whether or not it's inaccurate or not, it'll go through something called backpropagation. There's what's called an optimizer that determines how to do this. And basically the backpropagation goes back through all the layers and all the neurons in all the layers and determines how to adjust them for the next loop through the process to try to come up with a more accurate model. So basically, we've got this idea of a partial derivative, right? And this is basically how much to change a single weight. And this goes through and tries to figure out how to make it so we have the least amount of loss the next time we run through. And so this is a very iterative way to do it. We don't know how to create this function to determine whether there's cats or not in our picture. So we're going to create this big giant structure of a function to try to determine it for us via trial and error. And so this is that trial and error and repetition we talked about, I believe, in the third slide in the presentation. So we've got dense networks, and we've talked about the idea of a feed-forward network that only goes forward, and the data goes forward through all the layers and comes out with our neurons. That's great, but all the pieces of data in many ways are thought about individually. So if you've got our independent variables that you're passing in the case of a picture, all of our pixels, it really isn't taking a look at two pixels that are next to each other to see if there's any type of feature that you might be able to pick out of a picture. So when we're trying to figure out, given our prior example, whether or not there's a cat or not in the picture, it's really trying to come up with something that's looking at each individual pixel independently to come up with an answer. And believe it or not, it actually is not that inaccurate at doing it. But when you get very complex cases and you're doing facial recognition and things like that, you might actually start thinking, why I need to look at groups of pixels to try to pick out features that are relevant. And we're not going to get that in the type of machine learning that we've looked at before with our dense network. And there's a couple different ways that we can do this, right? So in images in particular, you might come across something called a CNN, and this is a convolutional neural network. And what it actually does is it pre-processes the data. And what it's actually doing is it's scanning across the set of pixels as they exist in a picture, which of course is a rectangular shape, and it applies a filter to it. And it just moves that filter across the picture and then down the picture and across and down the picture and across. And basically how big the filter is and how much it moves is all configurable. But the reason why you're doing this is you're trying to come out with an abstraction for a group of pixels, right? And then that abstraction of the group of pixels is then sent through the training algorithm. And the purpose behind this is to try to pick out features that are relevant, and the relevant features are then used to try to figure out the problem. Another type of neural network is something called a recurrent neural network, or an RNN. And so this is basically taking data and results that it's already gotten and feeding it into the next problem. And you might wonder why this is important. And it's important when you've got a sequence of data, and the result of the prior, or at least the data that's come before, is material to coming up with your answer. And so I don't know if you guys have ever gone and typed on your phone. I think most of us have. And you put in IMA, and it's got a bunch of words at the bottom where it's basically giving you some kind of thing that it thinks you might be typing next. You can just click on based on things you've typed in the past. And this is using something very similar to an RNN that's being trained for you specifically. And it's using the fact that you typed IMA in the past to come out with what it thinks is the most likely word that you're going to put in next. And so when you've got this idea, we've got a sequence of data, and the sequence of data is material to coming up with the answer, you might use something called a recurrent neural network. So there's a couple of other considerations that you might want to think about when you're creating your models and working with machine learning, particularly as a developer. So one, and I've touched on this just briefly earlier, is the concept of underfitting and overfitting. And I think for most people, underfitting is self-explanatory. Underfitting is when your data, or I should say your model, is not good at predicting the results, right? And so it can't predict your training data well, it can't predict your validation data, your test data, none of it. It's all very inaccurate across the board. That's something called an underfitted model. And we've got a little picture here on the left of what that might look like. And so basically it's predicted a very straight line relationship, mx plus b between the data. And so it's very bad based on if you give it a value over time on coming up with what the real answer is going to be. Now, the other side of that is called overfitting. And that's when the data is extremely accurate at predicting basically the training data and the validation data. And you say, well, that's awesome, right? And as it turns out, it's not necessarily awesome. And what I mean by that is it might be to the point where it's extremely good at testing your training data, your validation data, but then when you run it against the test data, i.e. data that it's never seen before in any way, shape, or form, it's very inaccurate. And so that's what the idea of overfitting means. And so overfitting data is where you have a model that's really, really, really good at predicting data that it's never seen before, and really, really poor at or I should say really, really good at predicting data that it's seen before, but really, really poor at predicting things that it's never seen before. And so what you're trying to do is find something kind of in the middle that's reasonably accurate, not only in predicting data that it's seen before, but in predicting future data. And that's kind of what we've got laid out in the middle, where we're trying to come up with kind of that sweet spot where it's pretty accurate. You know, maybe it's 95% accurate all the time. And once again, going back to if 95% accurate is a good or bad amount of accuracy, well, that really depends upon the problem you're trying to solve. So there's a whole bunch of cloud platforms out there, and you guys have probably heard of these, like Azure Cognitive Services, IBM Watson. AWS has a whole bunch of platform as a service offerings for machine learning. And so these are actually very interesting for those of us who are developers who don't necessarily know a ton about machine learning, right? You don't necessarily know how to put together a neural network or how to play with the hyperparameters or basically how to come up with a good model. And so these different services have platform as a service machine learning. For example, they've got Azure Custom Vision. And so what custom vision is you can pass it in your own collection of pictures that are pre-labeled, right? So we've got our 1,000 pictures of cats and not cats, and they're pre-labeled as being cats and non-cats. You can just basically drop them in to the online service, and it'll go through its training process because it knows how to do this type of classification with images. And then it'll spit out a model that you can now host in Azure that basically determines whether a picture contains a cat or not. And so each one of the vendors that do this, whether it's AWS or IBM Watson or Azure, there's a bunch of them out there. Google has their own versions of this, has some models that are offered as platform as a service that those of us who are not super adept at machine learning can just go in and with the maybe have some anomaly detection, you just pass it up some data and it'll tell you whether there's anomalies in it. And it doesn't require a ton of deep learning or machine learning knowledge in general. So this is basically, I call this training wheels on. And probably, you know, 3-4 years ago, this is where I was at with machine learning. I kind of understood what a classification was and regression and when you use one over the other, but actually putting together a custom model in TensorFlow using something like a neural network, I had no idea how to do that. And I've since learned how to do that. And that's where we're going on to the other side of the equation, which is more manual machine learning. And that's normally when you have custom problems that are very specific to your business, and it's not just something like determining whether there's a cat in the picture or not, or where anomalies are in a set of data. And this really requires kind of the deep knowledge of how to do this type of work. And it's not so much programming to create these models, it's more configuration and trial and error, and you're just trying to change configuration and retraining and retraining and retraining until you get a model that has a fair amount of accuracy and is not over or under fit. Now, you probably want to, when you're playing around with this hyperparameters, you probably want to do training with smaller sets of data so you can fail fast. And the reason why is because if you have a vast expanses of data, and based on the amount of calculations this has to do, you could have training situations where it takes days to go through the training process for a model. And so you want to be able to experiment in such ways that you can find out what is probably the optimal hyperparameters to fill into your model beforehand before you spend days trying to train it. The last thing is when you think about machine learning, there's a learning aspect of it, right? And this is basically making your model better over time. How do I make my model better over time? And when do I do that? You know, I don't know if you guys remember this several years ago, but Microsoft had put out a chatbot, and it was to try to mimic how a human will talk to people. And you could basically say whatever you want, and it got better at talking to people as it got more information about conversations that people were having with it. And it took about a day, I think, maybe it was 2 days before Microsoft took it down. And the reason why Microsoft had to take it down is, you know, people are people, right? They're a bit of scamps, and they train the model to be basically extremely offensive in a very short amount of time, because of course the model doesn't really have any kind of context around what is and isn't appropriate speech, and so they train it to be very inappropriate in a very, very short amount of time. So you got to think about how you're going to get your new data in, and who's giving you this data, and whether or not you trust them. It may be that if you're pulling in data from the public about the results of your model and whether they thought they were good results or bad results, and then you can use that feedback to retrain the model. You got to think about, are the people who are giving me this information, are they trustworthy, right? Or do I have to pre-process this data to kind of throw out the people who are doing teaching our chatbot in order to be very offensive? And that was a mistake Microsoft made, right? So they were getting great amounts of new data. They were training it with very little new data coming in all the time, but they just trusted the source of the new data without doing a lot of validation. As it turned out, the internet at large, not particularly trustworthy. So you got to think about where the data is going to come from. And if you do retrain the model and you're putting it out into production systems, how do you test it to make sure that suddenly this model is not less accurate than when it was before, or when it made predictions before with a reasonable amount of accuracy? Are there certain situations or edge cases where it's now very inaccurate? So you got to think about some kind of a test plan for it, because really what you're doing is you're coming up with a function, but the function itself is a black box. You've trained it, you know how you configure the function, but actually how the data is flowing through the function and what the exact hyperparameters are and how that impacts the weights and biases. Well, that would be, based on the thousands and thousands and thousands of calculations in there, that would be almost impossible to try to figure out on your own. And then you got to say, all right, so now I've got this new model. How am I going to distribute it? Is it behind a service, or basically everywhere where that uses this service, I just drop it in the service and everybody gets it immediately? Is it running client side? Do I have to put out a new version of my app? So you want to think about that as well. So going and retraining your model isn't an easy thing, because what we're really talking about is taking a function that's currently in production and modifying that function and putting it out to the public again, or whoever the users are of our application. And so, as we all know as developers, when we start making changes to our functions, we probably want to have a way to make sure that the data is coming out in a reasonable level of accuracy that's acceptable to the business. Now, I did put this together quickly. I'm not going to go through it in detail, but there's a ton of machine learning frameworks that are out there. These machine learning frameworks, some of them are easily usable to us, and I've determined that by putting the pass indicator on them. So when I say us, I'm talking about developers who don't know how to make custom models, right? So IBM Watson or Azure Cognitive Services, those might be pass offerings where we can go in. We don't necessarily need to know Python, for example. They're configuration type services. We can stand them up and run a model and retrain our model, all basically in a box that developers don't necessarily know how to use. On the other side, if you want to do something like make totally custom models using neural networks, then you might look at something like TensorFlow. And that's where you really have to have, or at least be a machine learning practitioner and understand how to put that in and stand it up. So just be aware there's tons of these machine learning frameworks out there and offerings. They don't all do all kinds of machine learning. So if you have something like I don't know, C#, you can write just about any type of application for C#, for example. TensorFlow is not like that. So TensorFlow in particular is very focused around doing neural networks in particular, using a framework called Keras, or at least an interface called Keras. And so if you want to create neural networks, either doing classifications or regressions, and you want to be custom and you're a machine learning practitioner, then TensorFlow might be something you want to look at. But if you're doing unsupervised learning, well, TensorFlow really isn't designed to do unsupervised learning. And also, if you look at something like Core ML, which comes from Apple, that's really designed in order to make models that run on mobile devices, for example. So you want to think about which one of these frameworks that you use for different situations. So that's my kind of developer's primer into machine learning in particular, and what all the concepts are in machine learning that you might come across, and how you as a developer can potentially use machine learning in your application. Thank you. I don't know if we have any questions for today, or we want to call it the end of the presentation. See if we got something in chat. Let me take a quick look. No questions. All right. So
actually, we did just get one that came in.
Oh, yes.
Have you learned how to hack the stock market? Smiley face.
So the question is have I learned how to hack the stock market? And so the great thing about machine learning is it can find relationships between data that most people don't have. And the good thing about the stock market is there is a lot of data in the stock market, but where you're going to fall down on that in general is the idea that when the stock market goes up and down, there's a ton of different factors that go into that. And not all of them are factors that we easily predict. And so when you think about our model, we have all those independent variables that are coming in. And when we do our training process, we'll have to come up with some set of independent variables that really is representative of all the stuff you need to know to determine whether a particular stock is going to go up and down. It might be based off of some information in their 10K or their annual report. It might be based off of news services, whether they have lawsuits. It could be all kinds of things. And I think the problem with creating that particular model would be knowing the data that you need to collect in order to do the prediction. Not that the machine learning model itself, the technology couldn't technically do it. I think it's just that we wouldn't be able to pick out and know with any accuracy what the data is that's material to figure that answer out. Now, I think another question was, how do we get into it? I'd start with using some of the platform as a services. And then I'd move over, depending on what type of a developer you are. If you're like a C# developer, I'd start looking at something like ML.NET and try to do easy regressions or classifications. And I brought up my example about 1 million times of doing cat or not cat. And I'd start with simple problems like that. I even just to play around with stuff when COVID was going on, I was doing regressions to try to predict basically COVID cases over time and how accurate I could get that. And of course, that's great because you always have new data coming in. And so that's the type of thing that you want to play with in order to get there. Now, I did not talk about the math. You're eventually, as you get deeper into it, going to have to understand more about the math. And the reason why is we talked about this idea of activation functions, where it determines how to, when it goes to that back propagation process, how to change the weights and biases. You're going to at least need to know mathematically what those are doing under the hood, because some of them work better for some situations than the other. I mean, you don't have to be an expert in the math, but you at least have to be able to understand what these different activation functions are doing. All right, anything else? Well, thank you, everyone, and have a great day.